Morning, everyone. I hope everybody is well. Today we're going to jump into the second part of the lesson about inverse relations and functions, and then I've got all queued up a set of questions to answer for you that you've been sending in on your homework. So that'll be produced as a separate video, but it's all queued up and it's going to happen right after this one. So first thing, remember we were talking about finding an inverse where you can switch the x and y value. However, yesterday we were just strictly showing this as a y, but if you remember, f of x is another way really of just saying y, but it's easier to work with when you've got a y in this spot than an x. When you put a little thing up here that looks like an exponent and it's a -1, we would call that f inverse, and it would stand for the inverse function of f. And it's what you get when you switch those y's and you solve for y. So this is sort of the same as yesterday, but with some upgraded notation, and then we have to take it a step further and discuss domain and range on top of it. So first of all, let's think about the domain of this original function. The domain is all of the possible x values that are allowed for this function. Now we're looking for the x values that will give you real answers. So in other words, I can't have a square root of a negative and get a real answer. So that means in order for us to have a quote-unquote legal x value, you need to make sure that x minus 2 is greater than or equal to 0. And when x minus 2 is greater than or equal to 0, it really means that our domain is all x such that x is greater than or equal to 0. So there's our domain. Our range in this case is going to not be able to be any numbers that are smaller than 0, because we're making sure that this is a positive number, and you take a square root of a positive, you're going to get a positive or possibly a 0. So the range in this case, the y's have to be greater than or equal to 0. So the f of x function value has to be greater than or equal to 0. Can't be less than 0. We're talking about principal square roots here. So you've got a nice little set of values in this function. Now, what we need to do next is remember about how we can find our inverses. And our inverse is found by switching the x's and y's. Let's take a look at that. Okay. First thing we do is we switch the x's and y's. Here's our original one. Y equals x minus 2. We switch them, it looks like that. You want to solve for y. So to undo a square root, you square both sides. Okay. So now we have x squared. You want to get, once again, you're trying to get y solved for, so x squared plus 2. And so what we need to do then is, instead of having y equals, we need to upgrade our notation a little bit and make it as f inverse of x. And it looks like that. F inverse of x equals x squared plus 2. Now the thing is, if we just had this on its own, we would be thinking about, okay, our new domain is x could be anything, and then y would turn out to be anything. But since it's specifically an inverse function of this, our domain and range are limited. And our domain and range are limited by looking at the original function and switching the domain and range. Okay, so here's our new notation. So we have our new function. Here's our original, here's our inverse, but we have to be careful with the domain and range for this. So that means that the domain of this one becomes the range of this one, and the range of this one becomes the domain of this one, but with the x's and y's switched. So here's what that looks like. Here, my range turns into my domain for my new inverse function, and my range turns into the domain from that one, and these are the values that are allowed, even though it looks like you might be able to have more values. You do have to limit it because these two are inverses. And remember, we said that the graphs on an inverse function have to literally be across each other on that that line y equals x. So there has to be, for every value on one side of the line, there has to be one on the other side. So if we don't limit this like this, you're going to end up with things that don't match up right. So inverses do have to switch the domains and ranges in addition. That's a big thing for you guys to get your heads around. All right, let's take a look at another one. All right, we want to find the inverse, the domain, and the range for this. Okay, so let's talk this through. Okay, first of all, the domain and the range for this one. Really, there's no square roots, there's no denominators to worry about. So x can be anything, so all real numbers. And so since you've got that infinite number of numbers you're plugging in, if you just take 6 minus 4 times that, you're going to get an answer every single time. So the range is also all real numbers in this. So just jumping ahead a little bit, reverse them. It's still the same. The domain and range of the inverse will still be all real numbers. What we need to do then next is you need to think of it as a y instead of a g of x. Then switch your x's and y's. And once the x's and y's are switched, then you solve this one for y. Subtract 6, divide by -4, and then simplify that thing. Remembering that when you have a fraction, you've got a denominator, but it applies to both of the things that are subtracted here. 1 over -4 is -1/4. -6 over -4 gives you +3/2 when you simplify it. So we put it into its proper notation then. The inverse of g of x, g inverse of x, is -1/4 x plus 3/2. So you've got, here's our inverse function, here's our original one. The domain and range are both all real numbers in both cases. So you're thinking, put in a y as a placeholder, switch them, solve, and get your new answer. Now what that leads us to is back to our composite functions. And I know that composite functions are fairly new to you guys, but there's a little trick that happens if you have inverse functions. And the little trick is that even without doing any work, if you take f inverse of f of x as composite, you're going to just get whatever the number x was. Same thing, this is the only time when composite functions aren't usually commutative, but in the case of the inverses, they're mostly commutative. And I say mostly because there is a little exception here. F inverse of f of x equals x as long as x is in the domain of f. So they undo each other just like inverses usually undo each other. Okay, so just like if you have 5 minus 3 and then you add 3, you get 5 back. Or you have, your add, subtract, multiply, divide, they all have their inverse operations. These are inverse operations. But we have to watch out for the domains. Remember, in a composite function, you're always doing this function first. So that's why you've got to watch out for the domain of that first function. In this one, you have to watch out for the domain of the inverse function, because that would be what gets done first. Now, what I'm going to show you is, I'm going to show you why it works in the form of an example. But then we're going to get a giant, massive shortcut that you guys are going to love, and you're always going to want to use the shortcut because that's what you should be doing. But I need to, out of good conscience, show you why it works. So we're going to use an example. Okay, so here's example problem, f of x equals 1 over x minus 1. Our domain is x can't be negative 1 because x minus 1, x can't be 1 because x minus 1 equaling 0 would be a no-no. So when x equals 1, that messes it up. So the domain is anything except for 1. And the range then would be anything except for 0. Okay, and we'll get to that shortly, okay, as far as why that's the case. So let's take a look here. Y equals 1 over x minus 1. We switch the values and we solve. We could multiply both sides times y minus 1. And then we can divide both sides by x. And then add 1. And here's the interesting thing is we really couldn't find the range of this one until we found the domain of this one. This one kind of popped in and I said I would explain in a minute why that's true. Well, here's why. Okay, our domain produces our range for this. But when we look at our inverse function, we find that 1 over x is part of it, which means x can't be 0. And so this domain actually backtracks and produces the range for this. So you're using one to produce the other, but then you have to look at your inverse to see if there's any restrictions that pop in for that. So your domain primarily comes from the first one, the original one. And then the range is going to come from the domain of the inverse. And that's just a good thing to keep in mind as you go through these. All right, so let's look at the two cases that I was talking about. All right, f of f inverse of 1. F of f inverse of 1. Okay, so if we plug in and turn it into this, you find the f inverse of 1. Okay, f inverse of 1. Well, here's our f inverse function. So you'd plug in 1 here, 1 over 1, which would give you 1, plus 1 is 2. Okay, so there's your value right there. This is f inverse of 1. F of 2, if we go back to our original function, 1 over 2 minus 1 gives you 1. And this is just a really quick way to show you that f of f inverse of 1 equals 1. If there was a 10 in there, f of f inverse of 10 would equal 10. F of f inverse of 896 would equal 896. So the f and f inverse undo each other, but there would be an exception, and we'll get to that shortly. F inverse of f of 1, okay? What we notice here is that f of 1 isn't going to work because the domain, okay, the domain excludes 1. And if you try to do f of 1 first, you're going to get a 0 in the denominator, which means undefined, and before you get very far in this problem, we get no solution. And so this is why that whole exception thing works. You're looking at this function first, checking out the domain and make sure it's not a restricted value. Okay? Now, you're not going to want to go through all this work, and you don't have to, because in general, f and f inverse undo each other so that you can jump straight to saying, oh, I know that this one is just 1 without doing any work. This one you would think would be 1, but always check the domain values of whatever function is, I'll say, closest to it, because that's the one you would do first. F inverse has no restrictions on 1, so you're good for the domain. This one does have a restriction. There's no solution because when you check the domain of f of 1, check the domain for 1, x is not allowed to be 1, so there's no solution. So our shortcut is just whatever this value is turns out to be the answer, except for those few times when you have an exception. So let's look at some others and do them by shortcut. We want to find the f and f inverse for these specific functions. So f of f inverse of 5 would have to be 5. Okay. I want you to think this through. Okay, because we looked at 5, and 5 is fine. F inverse of 5. The only thing that f inverse is not allowed to be is 0. F of f inverse of negative 27 is negative 27. Not restricted. F of f inverse of 0. Okay, f inverse has a restriction on the domain. It can't be 0. So that means this one has no solution. We switch the order though, and we look at f of f inverse of f of 0. We check out the domain up here for f, and that's perfectly fine. The only thing x is not allowed to be for the f function is 1. So this answer is just 0. And then f inverse of f, 85 is fine. So 85 is your answer. All right, I hope that all made sense to you, especially those last examples for our shortcuts, so that you don't go through and you don't do any work. Is when you see this, you're going to assume that it's going to be the answer, but then just double check yourself with this value that's closest to check for the domain, making sure that the domain restriction isn't keeping it from being that number. All right, so that's about it for today, and I'm going to get this video up, and then I'll work on your questions that you were asking on assignments 80 and 81, which was the last section that we did, section 6.5. All right, have a good day and stay safe.